right. Good morning, everybody. Go and get started today.
Good morning.
And then we're going to have a quiz later on today. I'll give you a link through GradeLink. I'll email it to you all, and also it'll be a post on GradeLink. It'll be a Google Docs quiz that you'll take. It'll be multiple choice questions, 4 multiple choice questions. There'll be 3 vocabulary questions or questions about concepts that we went through this week, and then 1 problem like your homework that I've assigned this week. So read through your notes and then homework problems to prepare for the quiz. It'll be very similar to what you've seen in your notes and on the homework. Any questions about that before we get started? Okay, so today let's finish up 11.2 and we'll start to review for the test coming up next week. All right, so if one ball is going, we'll say at 1 meter per second, and the other ball isn't moving, there are 3 things that could happen when the balls collide. So for the first case, after they collide, you could have the first ball move back to the left and this ball move to the right. This would be before collision, after collision. Can you all read all of that? Is there anything that's cut out?
I can read it all.
So let's say that after they collide and they go backward in different ways, that the one going to the left is going at a velocity of negative 0.2 meters per second. And it's negative because we're just saying that leftward is negative. And then the other one's going to the right with the velocity of 1.2 meters per second.
Oh, sorry, 5.
You would have 15.
Okay, so if that were the case and they were to go backward in these directions, we could find out the energy that they have before and after. And what we would see is that there's more energy after than before. So let's look to see what happens. So before the collision, kinetic energy of this ball would equal 1/2 mv squared. So we need to know the velocity which we're given in the mass. We'll just say that the mass is 1 kilogram. So kinetic energy would equal 1/2 times 1 kilogram times the velocity squared. So that would just give us 0.5 joules. Oh, now with sig figs, actually we need 3. So there should be 3 for this one as well. So 0.500 joules. After the collision, we now have 2 balls in motion. So over here, kinetic energy is just the first ball because the second one's not moving. But over here now there's 2 balls in motion, so you have to find both their energies and add them together to see the energy that they have in total. So for the first one, again, we do 1/2 mv squared. We'll assume these are all 1 kilogram. And so its velocity is negative 0.2 meters per second. Now we square that though, so you won't ever have a negative answer for kinetic energy. because anytime you have velocity and it's negative and you square it, it becomes a positive. So the answer will be positive. And we get for that 0.74 joules. So that's the energy of the first ball. We also need energy of the other ball too, because they're both in motion. So to get total energy of the system, we would need to get the energies of both of these balls, add them together. So for the other one, we would do 1/2 mv squared. We'll say these are both masses of 1 kilogram. Multiply that out. And we get 0.72 for that. Wait, I think I have something wrong here. Let me check really fast.
Miss Holly?
Yes, go ahead.
How did you get 0.74 for the first one?
I think that was a mistake. I read my notes that, but I think that's the wrong answer. What did you get for that?
0.02.
Okay, thank you. Yeah, I knew there was something that was right and wrong about that. So let me go back and fix that. Okay, so that one should be, what'd you say again for that one?
0.02.
0.02, thank you. Okay, so it actually should be 0.02 joules. And there was sig figs. Again, we have 2 here, 3 here, so we should put 2 here. So 0.020 joules of kinetic energy. And then this one has 0.72 joules kinetic energy. So the total amount, you would add them together. So that would give us 0.074 joules of kinetic energy. So we can see that after the collision, they have more combined energy than they had before. So before the collision, it was 0.5 joules. After the collision, it's 0.74 joules. So it's gained energy. And that's unusual. It only really happens if you have some kind of spring system set up here. So if the ball were to collide and a spring were to come out, or if there was some kind of explosion that took place, then that would happen. But outside of some kind of inside force that acts on the two balls, you won't see a gain energy unless there's some kind of explosion or spring or some kind of, something firing out. So because energy has been increased after the collision, it's called a superelastic collision. Let me go and get this for a second. Let me see really fast. Okay, sorry about that. Okay, so that superelastic collision, when you gain energy after the collision. There's 2 other things that could happen besides this one though, so let's look at the other cases. So what could also happen is that when you have one ball going at a certain speed, the other one's stationary, and they collide. is after the collision, what could happen is that the first ball that was moving just stops and stays in place. And then the other ball moves forward with the same speed the first one had. So in this case, there's a complete transfer of energy from one ball to the next. No energy is lost or gained. And so what we call this one would be an elastic collision. So an elastic collision would be a complete transfer of energy between objects. No energy is lost or gained. This happens most often in things that are hard, like steel balls or billiards balls, things that don't have any kind of give to them, things that aren't squishy, things that are solid, and when you hit them, they bounce right back. Does everybody have this down?
Not yet.
So for the quiz tomorrow, sorry, actually today, you won't have this on the quiz. It'll be anything before today. So it'll be things we covered from Monday and Tuesday. And it could be questions, again, vocabulary questions or homework questions, but it won't be anything we covered today in class.
So is it from all of chapter 11 or just 11.2?
No, it's 11.2. So just what we covered Monday and Tuesday this week will be on the quiz.
Okay, thank you.
Is the quiz going to be timed?
No, it won't be timed. No, it's on Google Docs and they're not timed quizzes. It's 4 multiple choice questions. It won't take very long, but there's no time limit. But you can only take it once though. So you have to take it in one sitting and you can't repeat it. But besides that, it's not going to be a time quiz. Okay, let's look at the last thing that could happen in this collision. So the first one, the balls bounce back in different directions. They gain energy. Next one ball hit. The second one, the first ball stopped. Second one went moving at the same speed of the first ball. The third thing that could happen is that the balls could squish together. So before the collision, again, you have one ball going at 1 meter per second, the other one stationary. After they stick together and go forward with one speed, so let's say they go forward with a speed of 0.5 meters per second. They would have lost energy in the process. So let's see what happens here. So kinetic energy to begin with would be 1/2 mv squared. We said again that the mass is 1 kilogram. So you multiply it out to get kinetic energy before the collision, and it would be equal to 0.5 joules. After the collision, what we have here, so these balls, because they're stuck together, are like one mass. And so we would add the two masses together, and we would have a mass of 2 kilograms since they each both weigh 1 kilogram. So we multiply it out, and what we would get would be kinetic energy of 0.25 joules. So it went from having energy of 0.5 joules to 0.25 joules, and so it lost half of the energy due to the collision. And so this is called inelastic, when energy is lost. So this usually is seen when you have squishy objects that deform when they're stuck together. You know, like clay, for example. You know, if you have 2 clay balls and you threw them against each other, they would stick and they would deform. So things that are squishy and don't have a definite shape, when they collide, would be inelastic. And they lose energy due to the deformation when they hit each other. Yep. But in all 3 cases we looked at, whether it was super elastic, elastic, or inelastic, there were no outside forces acting on the system. So we're ignoring friction. We're ignoring anything that, you know, any kind of push the balls would have been given. So there are no outside forces in this example. So momentum would be conserved in every case. So even though energy can increase with superelastic, stay the same with elastic, or decrease with inelastic, momentum would always be the same before and after the collision, as long as there's no outside forces acting on the system. So momentum is always conserved when there are no outside forces acting on the system. And that's what we assumed in this example. We assumed that there's no friction between the ball and the ground. We assumed that there's no air resistance, and that the only force, well, the only force would be gravity pushing down the ball, and it'd be counteracted by a normal force pushing up. And so there'd be no net force acting on the balls. Now, one ball does have movement, but that there's no new force. You know, it already had been pushed forward previously. There's no additional force after it's been pushed. And so there's no net force in the system. There's no change in the force in the system. So it's an isolated system. And we can say momentum is conserved before and after in every case, whether the balls are inelastic when they squish together and lose energy, super elastic where they gain energy. In either case, momentum would be always the same before and after, provided that the forces don't change. All right, so that is the end of 11.2. we'll start to review after this. Today I want you to work on a few questions on 301. Let me see really fast. So it's 22 through 28. All right, I'm here too. It's on page 301. And then sometime either today or tomorrow, do the quiz. And I'll give that to you through GradeLink. I'll post it after this class today. I'll email it to you all too. I'll email you through the GradeLink system. So you have your email address on GradeLink, you'll get an email. If you can't find it, just email or text me. I can give you the link through that.
Miss Holly,
Yes, go ahead.
is the quiz going to be our only grade once we take it?
Well, next week we're gonna have a test. And so we would have a quiz grade, a test grade, and then homework grades would also be included in that. So as long as you do the
Okay.
homework, I'm not gonna actually grade the homework, but as long as you do the homework, then you'll have a homework grade for there too.
All right, thank you.
You're welcome.
Miss Holly, could you explain how you want us to draw the bar graph? Because that's been a couple problems. I'm not really sure how we
Oh,
want to
sure.
draw this.
Okay, so what question was this one again?
23.
23, okay. So for that one, it says draw bar graphs to show the forms of energy present in the following situations at its highest point. So there's two kinds of energy he could have, potential and kinetic. So at his highest point, he's not moving. So it's all potential. And he has his highest height. And so it's max kinetic. And so you can just draw a bar graph that shows no potential energy at 0, no kinetic energy at 0, potential energy at its maximum point, which you could choose any value for. Let's just say it's 10. And then, so that would be for A. You draw a bar graph for potential energy at, say, 10 joules, 0 for kinetic. And then for B, at its lowest point, it's just the reverse. So he's lost 10 joules of potential, but gained 10 joules of kinetic. And so you just do the reverse. You show 0 joules of potential and, say, 10 joules of kinetic.
Okay, yeah, that makes sense. Thank you.
You're welcome.
Miss Holly, when did you say it was common for something to be a superelastic collision?
Superelastic would be if you have, like a spring that, shoots out, or some kind of chemical explosion. It's just kind of outside or internal force that happens during the collision.
Okay, but like in the example, if it was, they're like two balls bouncing off of each other?
Yeah, so you have to kind of like spring activated thing. Like when you hit the ball, a spring pops out, for example.
Okay, but two balls hitting each other wouldn't be a superelastic collision, right?
Not ordinarily. If it's just two ordinary balls with nothing besides just a regular ball, then that's right, it wouldn't be.